All right, so let me bring up the practice test key. Okay, so just like the quiz, exam is going to have some, tell me what the probability of the Z value is in this region. You have to have your Z table. I'll bring extras, but most of you, I would really rather you have your own so you can be practicing in the meantime. But this is supposed to be a slam dunk. Now remember, there's only 3 questions. There's only 3 possible questions. The probability that Z is smaller than something, the probability that Z is bigger than something, or the probability that Z is between 2 things. Everybody got that? Those are the only possibilities I can have. So what I have to do in each case is say, okay, if it's the probability that Z is less than that number, I look up that probability and I write it down. There's absolutely no work to do. Can't mess that one up. What do you do when it's the probability that Z is greater? Well, then you're given the right tail, but you want the left, so you have to subtract it from 1. And in the case where you're given the betweener, you take the bigger probability and you subtract the smaller probability and you get the probability between. That's it. That's absolutely 100% of the time what we're going to do. Okay. Now, before I move on, any questions on that? So, I don't know if you, oh, you know what? You guys can't see this very well, can you? Let me move this over a little bit. I realize there's a big glare in the middle of my screen here. Again, there's only 3 questions. The probability that Z is smaller than a number, the probability that Z is bigger than a number, or the probability that Z is between 2 numbers. Okay, those are the only possibilities. In the first case, remember, in the first case, we're basically saying, I want this, and I look up this in the table. I don't have to do any work whatsoever. I look the probability that Z is less than that number. The second case, we're asking what's the probability that Z is bigger than some number, but the number we look up in the tail is always going to be to the left, so we have to subtract it from 1 to get the stuff on the right. And in the third case, like I said, we want the between. We want everything between here and here. So what we do is we take the bigger probability and we subtract the smaller probability, and that gives us the probability between. There's not another version of the question, and most of you found that pretty simple. You know you have a bad answer when your probability is negative. What did I do if I got a negative probability? Does anyone know? There's only one way I can do that.
You
put it wrong with the calculator?
subtracted backwards.
You subtracted backwards. You didn't go bigger minus smaller, you went smaller minus bigger. You didn't go 1 minus number, you went number minus 1. The only way you can get a negative, like Salvador said, is to subtract backwards. So you know you messed up. Now, don't say my answer is negative this, oh, therefore it's positive this. No, fix it. You can't get a negative probability. Can you get a probability bigger than 1?
No.
No. In this case here, I'm taking the difference of probabilities. What if I'm kind of not paying attention and I add my probabilities? Would it be possible that I exceed 1 in that case? It's possible.
Yes.
Yeah. And then again, then I know, oh, you know, I messed up. I did something wrong because that's not possible. So those are supposed to be gimmies. Now, the next section, the next thing we did was, instead of me giving you, just simply giving you a z-score and saying, what's the probability? That's pretty easy. That's just, I look it up in a table. Next cluster of problems is now, what if, okay, now we have a situation. Okay, a situation. I like using IQs because their numbers are so friendly. But I give you a situation where we know the population mean, we know the population standard deviation, and we're saying, what is the probability of the following outcomes? Not the probability of the following z-scores. That means we have to convert to a z-score. So how do you convert to a z-score? It's always the same way. Score minus mean divided by standard deviation. So in this case here, I said, what's the probability that we're at least 90? Now, since 90 is below average, 90 or above should be the majority of people because exactly half the people are 100 or above. So 90 or above should be way more than half the people. That kind of common sense kind of tells you sometimes, did I subtract the right direction? Did I look up the right number? I'm asking for more than half the people. And so what we did was we changed our 90 into a z-score of negative 0.67. But because I wanted bigger than that, I had to subtract that from 1, as you can see on the screen there. Okay, so that's pretty safe. Now the next one, I asked you a betweener. I want to be between 85 and 106. Okay, so I find the two z values, -1 and positive 0.4. Always go 2 decimal places, even if that second decimal place is a 0, because you still have to look that number up in the table. And I want to make sure I have the whole thing in the table. Okay. Any question on 4 or 5, anybody?
Could you could you do like a quick example?
Well, that's what those are. I mean, what you mean a different example? Because
Yeah.
I mean, okay, let's just make up a different problem. All right. Okay, those are really good examples, but let's do one where we want to find the probability. Let's keep it with IQ because we already know the mean. It doesn't matter what the situation is. I like this one because we have integer values. There's no decimals. It's just easier to put in your calculator and stuff. Okay, what is the probability that a human being has an IQ, let's say, greater than, how about 76? What is the probability that a human being has an IQ greater than 76? Now, 70 is very low, by the way. So this would be the vast majority of all human beings, wouldn't it? Have IQs above 76? Anybody? No?
Yes.
Yeah. By the way, does anybody know what if you're below 70, there's a legal medical term? Does anybody know what that is?
It's the retarded, right?
Mentally retarded. That's the definition of mentally retarded. Your IQ is below 70. Because an IQ below 70 puts you 2 standard deviations below. So you're talking about a very, very small percentage of society. That's what in the medical profession is called mentally retarded. And I always like using this example. You guys remember Forrest Gump?
Yeah.
You remember what his IQ was? 75. So he was barely above that, but you remember Forrest wasn't the sharpest tool in the shed. Am I right? He was a little slow, but he was 75. So he wasn't technically automatically able to go to public school and do all that. His mama had to pull some strings, if you remember, kind of iffy at best. All right. So X being bigger than 76, what would my Z value be? Well, it'd be 76 minus 100 over 15. So what is that value exactly? What Z value will I be looking up? Anybody?
1.6, negative 1.6.
Negative 1.6. So negative 1.60. So I can say then the probability that an individual has an IQ greater than 76 is equal to the probability that a Z value is greater than negative 1.60. I need that inequality because that's what I'm looking up. Now, some of you try to do these without ever writing the inequalities. Problem is, greater than versus less than is a completely different answer. So I really need to write the inequality statement so I know which way I'm going to do things. Am I going to look up the number or am I going to subtract that number from 1? Because I want everything bigger than. So on my picture, negative 1.6 is very small. I want everything bigger than. So I want that. Remember, the table is only going to have that value. Agreed? So therefore, let's everyone look it up in your table. You tell me. I don't have a table right in front of me. What is the probability that Z is smaller than negative 1.60? So my answer is going to be 1 minus that number. So when you look up negative 1.60 in the table, what do you get? What probability?
0.0548.
Sorry, 0.
0.505
05
48.
48. Does everybody agree with that?
Yes.
So 1 minus that would be 9,452. So in English, 94.5% of human beings have an IQ above 76. That's what that means. And that makes sense because 76 would be a very low IQ. So the vast majority of people should be above that number. So this is it. The difference between this and the first thing is we had to figure out the z-value and then we look it up in the table, but that's not complicated. Now, the next piece of the puzzle is where it gets a little bit more interesting, because now I'm not asking for an individual. I'm saying I went out and collected a sample and I asked the same question. Now, what we're doing technically, the first two problems, we're doing a sample of size 1 because we're asking for an individual. Now I want a sample that is not 1. So in that case, what do we do? Well, Z is computed a little differently. This goes back a few weeks ago when we talked about something called the central limit theorem. You don't have to remember the name, but what it means is the Z is still score minus mean over sigma. That part didn't change, but now it's sigma over root n because the sample size matters. So let me show you the picture here. I know I'm going back and forth, making you all dizzy. So formula, if I have a sample that is not 1, I have to actually count for it here. Now, if the sample is size 1, you have 1 person, then you have the square root of 1, which is 1, and then we basically just have the original formula. But if I have a sample that's more than 1, I have to divide sigma by the square root of n. That's how I get my z. Okay, so in the next example, I asked you for same problem. I went out, collected a sample. I want to know what's the probability of an IQ greater than 105, but not for an individual, for an entire sample mean. So therefore, I do the same math, 105 minus 100 over the standard deviation, but instead of divided by 15, it's divided by 15 over root 40, which changes things drastically. So that's actually the most common situation because nobody goes out and collects a sample of size 1. We collect a sample of size n, and n is probably bigger than 1. N might be huge. The only thing I do differently is I divide by the square root of n. Now that's on your formulas, so you want to make sure. Now on the exam, and I will remind you guys, I'll send out an email probably Monday. You got to have a calculator that you are comfortable with. I will bring them, but you're still better off having one that you're used to using. Have your Z table. That's the only one you need. We're not doing chi-square on this test. And have the formula sheet. And I'll remind you which part of the formula sheet's actually relevant. We don't need all of it, but we do. There's 2 pages so far that you probably should have both of them with you at all times just to check. And then you look things up. Yes, you have to do a calculation on your calculator, but the calculating is very little, isn't it? Part of it is just reading the right number. So in this problem, number 6, the only calculation I do is to calculate that z-value. Then I'm looking it up in the table, okay? And then the second one, both 6 and 7 are basically the same question. I'm asking you a question about an entire sample as opposed to one individual. So our formula for one individual, you could think about it as dividing by the square root of 1. It's overkill, but a lot of people will do that. They'll just put the square root of 1 in there. So a lot of folks, what they'll do when it's a sample of size 1, they'll do this, which doesn't change anything. But that way, if it were a sample of size 10 or a sample of size 100 or a sample of size 1,000, I put that number in here. That's a safe way of thinking about it, okay? Because 1, I'm not gonna mess up the 1, but it reminds me to put that in there for everything else. All right, any question on that stuff before we move on? You guys all good with that? All right, let's go to the next.
It's always basically following the same procedure, no, to get the answer.
Yes, yeah, that's why when we're doing these problems, that's why you want to practice them so you don't have to think about them, right? Now, number 8, very important question. By the way, we've mentioned this once before. What is the organization Mensa? What is that organization known for? Does anyone remember? It came up right when we started this process with IQs and things. You've all heard of the organization Mensa? Anybody? It's okay if you haven't. How many have heard of Mensa? You guys are all muted.
I don't.
I've never heard of it.
You've never heard of it? Mensa is an organization of people with very high IQs. And, you know, some people brag, yeah, I'm a member of Mensa, you know, that kind of thing.
Yeah.
Okay, that's it. now I believe you have to be in the top, it's something like the top 2% or something like that. I can't remember exactly. It's just not that important to me. So we have a different organization. We want to look at the people who are in the bottom 20% of society. So that organization I affectionately will call Mensa. Mensa are the high IQs, so Densa would be the low IQs and dense. So where would the cutoff be if you're in the bottom 20%? Oh, that's an interesting question. So this is where now we have to go to our Z table. Okay, so pull out your Z table for a moment. And in your Z table, what you need to find is the probability that is the closest to 0.2. You're not going to find 0.2 exactly, but you need to find the probability that is the closest to 0.2. Okay. And if you hang on just a moment, let me do this. I'm going to go ahead. I'm going to bring that up on my computer screen. Give me just a second. Okay. Now let me go back to here. Now let me go to here. All right, took me a second, but here we go. So on my Z table, I'm looking for the probability that is closest to 0.2, and I think I see it right here. Does everyone see 2005? 0.2005. Of all of the numbers on this table, that is by far the closest 0.2. 0.2 being 20%. Everybody cool with that?
Mhm.
Now,
Yes.
what Z score corresponds with that probability? Let's see, it would be, lost it there. Where's 0.2? Oh, here we go. So it'd be -0.84.
4.
Okay, everybody
Oh,
agree?
okay. Yes.
So this is the one time we work backwards. Normally, we're given a Z score, we look up a probability. Here, I'm giving you a
Okay.
probability, and we're looking up the Z score. So the Z score of -0.84, okay? That's the Z score I want. Whoops, let me go back to here. So the Z score of -0.84. So look at my calculation here. You see, probability of being smaller than -0.84 is 0.2005. That's what we're saying. So we know that's the best number to use. So now if I say, what score do I need? I'm going to work a little bit backwards. Now, let me go back to, I know I'm going back and forth all over the place. How do I find a score when I know a Z score? So remember, if X minus mu over sigma is equal to Z, how do I get the X by itself? Well, that's easy. First, multiply both sides by sigma. Then I have X minus mu equals Z, X minus mu equals sigma times Z. Now add mu to both sides and I'd have this. So if I know mu, I know sigma, and I know a Z, I can tell you what score you need. Okay, so I'm just working backwards. Usually we have these three numbers and we're calculating Z. But I started by saying, no, I know what Z is, I know what mu is, I know what sigma is. What score does an individual have to have? So we said, there's my 100, there's my 15, and there's my -0.84 that we just looked at on the table.
Professor, just a quick question. Mu is always 100, correct?
For IQ. These are all
Okay.
IQ problems. I like using IQ because it's friendly numbers. Just put it that way. By the way, is it universally important that you understand IQs? Oh, heck no. It's just a really convenient way of doing what we're doing because the numbers are so friendly and so easy to put into our calculators. So going back to the problem now, looking here. Oops, let me highlight it there. Whoa, didn't work. It won't let me highlight it. Okay. So probability right here, Z is -0.84. So X is 100 plus sigma times the probability, or excuse me, times the Z score, and that gave us 87.4. That would mean that IQs below 87.4 would put you in the bottom 20% of society. IQs above that would put you in the top 80% of society. It's actually that simple. Okay. Now, next group of problems. Now we're going to use the binomial. We wanted to be able to do the estimations using the binomial without having to do all the large calculations. So I said we have a 250 multiple guess test, 250 questions, 5 responses to each question. That means your probability of guessing correctly should be 1/5. Your probability of guessing incorrectly should be 4/5. So if I should get 1/5 of all the answers right, then I should get 50 answers right. That's why my mean is 50. 250 times 0.2 or 1/5. Remember, the variance is NPQ, so the standard deviation is the square root of that, which in this case turns out to be the square root of, you see 250 times 0.2 times 0.8, that's the square root of 40. And I'm going to leave it as square root of 40. There's no reason to calculate that with my calculator. I'm going to do the calculation later anyway. To round that off prematurely and then re-enter it and stuff, it's too much work. I'll just leave it like that. So now I want to take that 250 guess question or question guess test, and I want to know what's the probability that I get between 40 and 65 correct. That means I need the probability of 40 plus the probability of 41 plus 42 plus 43. That's a lot of calculations. That would actually be 26 separate calculations where I'm doing combinations of 250 choose. Well, you know what? My calculator probably can't even do those calculations. I might need a supercomputer to actually do those ridiculous number of calculations. So instead, what we're going to do like we did in class, like you guys did on the quiz. The idea that, think rectangles. And we're doing that thing with the rectangles. I'm literally asking you, what's the probability of each outcome? Well, if each rectangle is of width 1 and its height is its probability, then I got to add up the probability of the 40, the 41, the 42, and so on, all the way down the line. That's an absurd number of calculations. But the rectangle that corresponds with 40 right answers, doesn't it start at 39.5? Remember that? Because it's going from 39.5 to 40.5. And then the next one's going from 40.5 to 41.5, because 40 is in the middle. Now, the last rectangle should be the rectangle that corresponds with 65 right answers. So where does it end?
65.5.
65.5. So I'm adding 0.5 at this end to finish the rectangle. I'm subtracting 0.5 from this end. So this one here ends at 65.5. So here's the beautiful thing about this. If X is between 40 and 65, then it's also between 39.5 and 65.5, because I haven't started into my next rectangle yet. And those are the values that we're going to calculate the z-scores for. Okay, we're going to calculate those two z-scores, and then we just make it a betweener. Oh, the probability that z is between this and this, I look up exactly 2 numbers in my table. I don't have to do a humongous calculation with factorials and all the gnarly stuff that we did on the last test. We don't have to do that because the problem is so big. So I do this. So I'm going to go back to my screen because I got all that put on there.
My practice test has different questions on it.
Oh, different questions?
Yeah,
Oh,
it says 100.
Oh, you're kidding. Means I edited it, but I forgot to change. Okay, well, let's go with this one because it's more interesting. So I have the key right in front of me. I am notorious for making changes and then not keeping track of them. Okay, so let's look at this for a moment. We said, look at this line here. Probability that X is between 40 and 65 is the same as it's between 39.5 and 65.5. We said the mean was 50 and the standard deviation was root 40. So all I've got to do is calculate 2 z-values. That's it, just 2. Lower z-value, 39.5 minus 50 over the square root of 40. You see that? That's the z-value of negative 1.66. And then on the other side, 65.5 minus 50 over the square root of 40. That's the z-value of 2.45. Now, when I look those up in my table, I don't have to do any more calculating. There's no binomial probabilities for me to calculate. We get 0.9444. if we actually had a powerful enough computer to calculate the probability of 40 plus 41 plus 42 all the way up to 65, do you know what? We would have gotten the same answer to 4 decimal places. Isn't that crazy? That's what's so beautiful about this particular thing. We say when n is huge, it's way simpler we in class we said, look at the rectangles and kind of blur your vision and you see the normal curve, don't you? You see the normal curve when you look at those rectangles. So I'm using the normal curve. It's technically called an estimation. It's not an equals, but for all practical purposes, it's pretty much the same number, but I don't have to do anywhere near as much work, and I don't have to have any fancy technology to do it. That's why it's so important and so powerful. Okay. Any question on that one? And by the way, one of the questions I have for you guys, how do you know when you're supposed to do this thing? Because before we didn't do this, before we just calculated z-score, right? Before we just said, well, you know, I'm asking you a question, we look up a z-score. How do I know when it's a binomial and I'm supposed to do all this? Well, the instruction is use the normal distribution to estimate. You have a binomial experiment and I'm asking you to use the normal distribution to estimate. That's how you know to do this. That's the only way the question will ever be worded. Like number 10, use the normal to estimate. Okay, that means I'm gonna, rather than calculate the area of all my rectangles, which would be mind-numbingly long and difficult, I'm gonna pretend like it's a normal distribution. I'm gonna pretend those rectangles look like a curve.
Where do we get the 50 again, Professor?
Where did we get what?
50 in the equation.
Look at question 9.
Oh, these are not too loud. Okay, my apologies.
There's 250 questions. You're going to get 1/5 of them right. So you're expecting. Remember, it's also called expected value. You're expecting to get 50. So this is true basically in every area of life. I mean, if you're a gambler, okay, you guys are probably not professional gamblers, because if you were, you would have taken this class a long time ago. Professional gamblers don't now take statistics. They probably already know their statistics. But you're a professional gambler, and let's say you like playing the roulette wheel over and over and over and over again. Okay, that's your favorite thing to play. And you only bet red and black. Okay, that's just you're kind of a lazy gambler. Well, there are 38 squares on the roulette wheel. 18 are red, 18 are black. So you have an 18 out of 38 probability of guessing correctly, and it never changes. So if I played it, let's keep it simple. I play it 38,000 times, then I ought to win 18,000 times, because my probability of winning is 18 out of 38. That's what I should see in the long run. Okay, that's, again, we've referred to that before. It's called the law of large numbers. When you do the same thing over and over again, what you see is exactly what you're supposed to see. So in a 250 question test, you should get 50 right if you're guessing on every single question. Can you get a little higher? Sure. Can you get a little lower? Sure. And then the question is, what's the probability of being in this pretty big range? Well, look at that. It's over 94% likely that you're going to be in that range. You're not going to get 250 right. You're more likely to be struck by lightning than to get them all right. Hopefully that, none of you are going to get struck by lightning, but that'd be below average. Okay. Now let's move on to the last group of questions, which are the confidence interval questions. Now these are completely unrelated to the thing we did before. So there are 5 lectures on this test. A lot of it is just simply looking up stuff in the Z tables. Now here is where you need to have your formula sheet, because on the formula sheet, if you remember, I call them the magic numbers. I don't want you to look these numbers up. I want you to have these numbers right in front of you. For example, the Z that corresponds with a 2.5% tail, that's the one we've used the most often. I bet some of you already know that one. Does anybody know that one without looking at it?
0.005.
Well, no, the Z value. Does anybody think?
Oh, sorry. That's 1.96.
Yeah. And by the way, in any stats class I've ever taught, by now every student in the class has that one down, because that's the one that they use the most often. They don't have to keep looking it up, but I do not want you to memorize them. Have the sheet, and I would probably, to be smart, take a highlighter. Just highlight those so you don't have to search for them. There's only 4 numbers that we ever use. So if I said, what's the Z that corresponds to the 0.5% tail? That was 2.576. That's a constant. You're just going to use that number. You're not going to look it up. You're not going to calculate it yourself. A computer did the work for us. And we're saying, thank you, computer. That saved me a lot of time and trouble, because that would have been a gnarly calculation for me to have to do on my own. But I know that's the correct value. So when you're doing confidence intervals, you need the magic numbers, we call them. Okay. And these are probably the ones you're going to use only for the confidence intervals, because this corresponds to a 0.5% tail. That means a 0.5% at each end. So it's a 99% confidence interval. This is a 2.5% tail, but that's 2.5 at each end. So that means it's a 95% confidence interval. So you might want to write that down on your formulas. I'm going to put the 95% confidence interval, the 99% confidence interval. For confidence intervals, those are the only two you're going to use. The other two numbers we use for something else that's coming up next after this test. But those are the two that you're going to use the most. Everybody cool with that? Hopefully.
Yes, sir.
1 second, please, Professor. Can you step aside for a second?
Yeah, what are the percentage?
Hold
I
on,
didn't-
hold on. All right. Well, can you, in a 90, oh, is that glare?
1.96 is 95%.
In the 95% confidence interval, that means 2.5% at each end. That's why we look up 0.25, because that's it, therefore at each end. So the 95% confidence interval is going to use this magic number. The 99% confidence interval means I have 0.5% in each tail. That's why I use this number. That's it. There's no other possible numbers you would use. And that saves us a lot of time and trouble, which is why I said on your formula sheet, I would literally take a highlighter, you know, so that when I'm glancing around, they're just right there. It is very likely that some of you already know those two, because we've used them so many times in the last couple of weeks, haven't we? It's very likely some of you actually know them. I don't need you to know them, but I need you to know how to get them quickly. So when you're doing the problem and it's 1.96, you're going to say to yourself, yeah, okay, I knew it was 1.96, but let me make sure, let me look it up, you know, on my table, excuse me, on my not my table, my formula sheet. I don't need you to go back to the Z table. We already did that. That's how it made it to the formula sheet. We did all the heavy lifting a couple of weeks ago. We found those magic numbers, and now you see them on your formula sheet, so you don't have to look them up again. What you would have to look up, if I said just for fun, you know what? I'm going to start my own company, and I'm going to make everybody take some form of a placement test. And I want to hire everybody who scored in the top, just pick a number, the top 2%, the top 10%, the top 20%. I want to pick everybody who scored in the top whatever percent. I would have to go and look that up in the table and figure out what Z-score it corresponds to. Kind of like what we just did with DENSA, which was the bottom 20%. I would have to look that number up, because that's not a number I know off the top of my head. But I do know the number for the top 2.5 or lowest 2.5%. That's the 196. I know the number for the top 0.5% or bottom. That's the 2.576. And those are the ones we generally use for confidence intervals. Okay, so let's do this. Let's look at this one. So the randomly selected 1,000 customers, 627 say they were satisfied with the service. That's such a big sample that you're going, you know what? Okay, this is good. What you're trying to do is say, well, what is the true probability that somebody is happy? I sampled 1,000 people. So I think the absolute true probability is probably close to that number. This is exactly the same as Rosalind's going to go out and shoot 1,000 free throws, and she made 627 of them. That's exactly the same question. Then what is the true probability? Well, I need an interval. I need a plus or minus. Okay, it's the same question exactly. So P hat down here, P hat is the measured or the experimental probability. I don't know what the true P is, but I know the true P is going to be that number plus or minus a cushion. Okay, now I need the value of Q hat. So you notice right next to it, Q hat is whatever's left over, 1 minus that. So if P hat is 0.627, then Q hat's got to be 0.373, because they have to add up to 1. Now my error, I know it's P hat, Q hat over 1,000 inside the square root. Okay, that formula we have on the formulas. Notice in front, I have the magic Z, the 1.96. Why am I using that number? As I said, 95% confidence interval. What if I had asked for 99% confidence interval? What would you have used?
2.576.
Exactly. There's no other question that really would have been asked. Okay. You calculate that, you got 0.30, 3 decimal places. So the true probability is somewhere between my 0.627 plus and minus. That's my cushion, plus or minus. And so my final answer is the actual interval that has the P right in the middle. And your measured P, your 627 out of 1,000, your experimental P should be smack dab in the middle. Now, the nice thing is when you're doing a sample, when you're conducting an experiment, I asked 1,000 people. Would it have been practical for me to ask 993 people or 1,013 people? Would that have been practical? Think about this for a moment. My P hat is divided by 1,000, so I have a nice, happy terminating decimal. It's really easy. I don't even have to use a calculator. If I pick some weird random value for n, remember, I'm doing the sampling. I can make n whatever I want. But if I pick something weird for n, then I get an icky fraction with a nastier decimal that I have to do more work. So when I'm sampling, I'm going to pick samples of size 100 or 250 or 500 or 1,000. Does everybody get that? I want to pick samples where my denominators are very friendly and easy to work with, so that whenever possible, I get nice terminating decimals. I don't have to round anything off with my calculator. Now, when you're calculating the error, no, you're gonna have to round that off because it's a square root. The numbers that went into it were very, very friendly. Now, the last question. This is the one where we were determining sample size. Now, there are 2 formulas on your sheet. And it's very important that we distinguish the 2 formulas, okay? One formula was if I had prior knowledge, okay? We talked about this, for example, with opinion polls. If every single few days we're doing a new opinion poll, all we have to do is use the numbers from the last opinion poll, right? The last P hat and Q hat we used. So whenever you're doing this type of problem, if you already have information, you use that number. What do we use if we have no idea? It's the first time we've ever asked the question. Do you remember? We pretend P and Q are both 0.5, which is 1/2 times 1/2. And then that 4 just shows up in the denominator. And it gives us a very simple formula. I'm going to go back to. So hang on just one moment here. Let me get out of that one. Let's see. Hold on, let me go here. Do I have? Give me un momento. On the screen here. Here we go. Okay. So we take this. I can't have everything pre-saved. I have too many icons on my screen. All right. So this is the set of formulas here. Okay. Now I want to go to the sample size one. All right. So here is the sample size. See, sample size determination. This is the one we just did just now. Using previous information, we used the 0.627 for P hat and the other number for Q hat. That's if P hat and Q hat are known from prior knowledge. But if I have no idea, we're going to go out and conduct an opinion poll of Mesa College students to find out how they feel about a certain thing, but we have no idea. We've never asked the question in our entire lives. Then it's reasonable to go ahead and start with P hat and Q hat, just assume they're both 1/2. If they're both 1/2, 1/2 times 1/2 is 1/4. You notice that 4 right here. No P hat and Q hat on top because I treated them both as 1/2. This formula right here is actually easier to use. It's the formula you would use if you had no prior knowledge. Okay, everybody okay with that one? We've done this before. If I have prior knowledge, I use the first one. If I have no prior knowledge, I use the second one. So let me go back. Let's see, which one do I want? Let me go back to the problem. Okay, so in this one here, look at the last question. I have prior knowledge, so I used 627 and 373. I have a really big sample. Just for fun, let's suppose we don't have any prior knowledge. So I have never asked any person their opinion about this restaurant. So I need to know how many people to ask to ensure that our error is no more than 2%. So I'm going to do the same thing. Hold on. Okay, I'm going to do the exact same thing. Right now, in this problem, we put p hat and q hat right here. Okay, in this problem, I have the 0.02 squared, I have the z value squared, and I have p hat, q hat. If I have no idea what p hat and q hat are, treat them both as if they were a half. And then what happens? A half times a half is a fourth, and that 4 goes down here. That's why that 4 is there. It's a half times a half. And then I would use that formula. So what would we get if we did this? Okay, so let's do this. 1.96 squared, 0.02 squared. I get exactly 2,401. If we said, I want to go out and survey the customers at this restaurant, but I have no idea what they're going to do. I have no idea how many to ask because I've never asked them before. Then if I want to minimize my error, I want to make my error no more than 2%, I need to ask at least 2,401 customers. When I had some prior information, or when I had prior information, I only needed to ask 2,247. Oh, the more information I have, the less people I actually have to ask. That's how it really works. Okay. So that's an interesting question. And again, you want to have that table. All right, let me go back to you guys now. Does anybody have any questions at this point on any of those problems? Because those are very standard. We did those in class. We did those on the quiz. Most of you did a pretty good job. But remember, it's spread out over a long period of time, and most of the stuff is before spring break. So that's going to be your biggest dilemma. Is it goes back an extra week because we had a week off. I gotta make sure I remember that.
I had a question.
Yes.
So for questions 12 and 13, on question 13, you use 1.96 for what reason? Because you used it in the previous problem, or for?
Oh, okay. Hold on a minute. Let me go back to the share screen. Hold on.
You see, it says how many customers.
Oh, right. Assuming, yes, that is an excellent question, because you're right. That is a little bit ambiguous. I apologize, because the first question said we want to construct a 95% confidence interval, and we had an error of essentially 0.030. That's 3%, isn't it?
Yeah.
Our error was 3%. So I said, you know what? How many people do I need to make it 2%? So we'd assume essentially the same information. You notice we used the same p hat and q hat. So it's reasonable to say, yeah, let's use the same z, because it's really the same question. But that's a good question.
I figured, but
let me change the problem. Let me change the problem. Start with, from a random sample of 1,000 customers at a restaurant, 627 say they're happy with the service. Now skip question 12 altogether. Just go to question 13. How many customers should I interview to have a maximum error of 2%? Every part of that quotient would be the same, except you wouldn't have known to use 1.96 unless I somewhere introduced the 95%. Does that make sense?
Yes, that makes sense.
So I would not ask 13 independent of 12, but if I ask question 13 without ever asking 12, I need to say a 95% confidence interval. But because 12, we were already working with that, it's reasonable to assume it's the same thing. It's all the same information.
I figured. Question. I just wanted to be 100% sure.
No, that is an excellent question, because the one thing nobody wants is ambiguity. Because with ambiguity, you're saying, well, I think I know what's going on, but it might be something else. I'm not really sure. By the way, it is never wrong to ask for clarification on an exam. I have people all the time, they'll be looking at a problem and they're kind of stressed and are saying, okay, I'm looking at this problem. Is this what you're asking for? I'll go, yes, that's exactly what I'm asking for. But that's a good question, because if you're looking at something and you're not absolute, you know how to do the problem. but you're not absolutely sure what's being asked for because maybe the wording is just confusing enough that you're saying, wait, am I looking for this thing or am I looking for this thing? It's always okay to ask. Your instructor's not going to do the problem for you, but they're going to point you in the right direction to make sure that if you know how to do it, I want you to get it right 100% of the time. I don't ever want you to question that.
Would you say, Professor, if we do this quiz and we know each problem like the back of our hand, we're able to solve it even with different numbers,
Well,
that we'll be all set?
Let's say if you do the practice test and redo the quizzes, that gives you a bigger sampling of the types of questions that you'll be expected to know, okay? See, if you only did a couple of problems, say, oh, I have the entire concept down, I did 2 problems, probably not enough. So if you do the quizzes, and by the way, I say this in every one of my classes. Every class I have, I give a practice test and we have a review going over the practice test. But I always remind them they have 2 sets of practice tests. You see, you also had your quizzes with quiz keys. So it is wise to always retake your quizzes and say, okay, I got 100% 3 weeks ago or 4 weeks ago. Do I still know it today? Or if I missed it a couple of weeks ago, have I figured it out today? So it is always in your best interest right before a test to redo your quizzes as extra practice because I give you a key. That's why I give you an answer key. So between the quizzes and the practice test, you will have covered every conceivable way a question can be asked. And you notice they're kind of the same questions, aren't they? There's really not that much variation. You go, okay, if I can answer this, I'm probably in good shape. Okay, there are a lot fewer questions on the practice test because the practice test, the idea is I'm giving you a fairly short summary of what we did. But if you go back and look at the quizzes, there are more questions because you have time. You have a week to do just a few questions. I can ask you more. On a practice test, I ask you less of each thing just to say, okay, I got this, I got this. Think of the practice test as I got this topic, I got this topic, I got this topic, but I'm only asking you one question at a time. Just because you get one question, does that automatically mean you can answer every version? Maybe, maybe not. That's where practice is really important to practice. And that's where the quiz can come in because you got that extra practice. So between the two, now it is very necessary from your point of view that you're not still practicing on Monday or especially Monday night. You got an exam first thing Tuesday morning. If you have uncertainty on Monday night, you're not going to fix it Monday night. But far worse, believe it or not, you can feel pretty comfortable with something today and then run into a problem that stumps you on Monday. Has anyone ever done that? Run into a problem that stumped them at the last minute? What does that do for your confidence? Down the tubes. So a problem that if I gave you the test today, you'd get it right. But if I give you the test on Tuesday, you'll miss it because you now just shattered your confidence because you ran into something that stumped you. So that's why I tell people never be doing review right up till the last second. If you don't know it when you go to bed Monday night, I'm sorry, you're not going to wake up Tuesday morning knowing it. That's not going to happen. But if you know it on Monday, you can still confuse yourself by running into an extra problem that you hadn't looked at. And now you can shatter your confidence. And that's the worst thing you can do, because if you know how to do something, you're not going to change an answer. You're not going to question it. You're going to write down and go, I know that's right. But if you're uncertain, I can't tell you how many times it happens. It happens every exam that somebody will erase a perfect answer on any test. They'll erase a perfect answer, not because they thought, you know what, I don't deserve this many points. Let me erase that perfect answer. No, they erase it because they no longer trusted it or believed it. That's because of a lack of confidence. They wrote a perfect answer, but they weren't confident, so they erased it. They didn't replace it, they erased it, which is really silly. So now it's a 0 where before it was perfect. Never change an answer because you think it's wrong. You only change an answer when you actually see the error. I see the error. Oh, now let me fix it. We talked about this before when Salvador said the only way you can get a negative probability is really subtract in the wrong order. So you saw, oh, shoot, I have a negative probability. Let me fix that. But on another problem, you have a positive probability. You don't say, I just don't like that answer. Let me erase it. That's foolish because you're not replacing it. You only change something when you know what to change it to, not because you don't like the answer. Can you imagine filling in a multiple choice test and saying, I have way too many B's. Let me erase all my B's, Now, I'm not going to fill another letter and I'm just going to erase all those circles that nobody would do that. That's completely insane. But that's what we're talking about here. If you erase an answer without seeing the mistake or replacing it, you're basically removing points from your total score. So don't do that. You know exactly what's on the test. You want to be totally prepared really at the beginning of the weekend. And then you got other stuff you got to do. You know, you have other classes. Some of you, I've heard rumors. Some of you have lives. Maybe even jobs. Does anyone here have a significant other? I know Raj
Nope.
does. But see, your significant other doesn't want to
That's a
find out
job.
that
That's a job. That's a job.
but you don't want your significant other to say that you're married to stats, right?
Our anniversary was on Monday, so we're celebrating this
Last
week.
Oh, congratulations.
7 years.
Congratulations. That is
7 years.
awesome. Wait a minute. Isn't that the 7-year itch? Isn't that what that's called? Have you heard that? Don't
No,
bring
I've
that up.
heard 7 equals completion.
But when it comes to you've heard the term 7-year itch, haven't you?
Yeah. No, that's not going on.
Okay,
Mm-mm.
because you know that term only applies to marriage when people talk about it.
Thank you, Professor, for the review. I
All right.
appreciate it.
At 7 years, I had
Thank you so much. Have a good one.
2 children at 7 years.
Thank
So
you.
I had gotten, I had no itch.
Bye, Professor.
All right, you guys have an awesome
Thank you.
weekend and relax, have some fun. Don't get in trouble or don't get arrested. Okay, get in trouble. Just don't get arrested. That's okay.
Thank you, Professor. Have a good weekend.
All right, guys, we'll see you. Stop recording.